It's my pleasure to have Dr. Lee here from GE Global Research to talk about the aerodynamics and aeroacoustics design of wind turbine blades. Dr. Lee got his PhD from Penn State in 2009 and then was a postdoc at Penn State and joined GE Global Research Center in 2012 where he's currently this is one of the areas of research he's doing, but he's also working on, we talked about this morning, aircraft jet engines and also aircraft propellers. So that's the kind of a neat thing about being at the Global Research Center. You kind of get involved in a variety of research activities. So with that, I look forward to hearing his presentation.
Thank you, Professor Van Dam. So today I'm going to talk about wind turbine blade aerodynamics and aeroacoustics. So maybe I can start with introducing to you GE Global Research Center where I'm working now. So I can see many graduate students here. So this information might be interesting to you students for your future career plan. So GE Global Research Center is the first US industrial lab. It started around 1900 in upstate New York. And so we are doing fundamental scientific and applied research that have commercial application to all GE products. And right now, more than 3,000 engineers and scientists are working at 5 global research centers. So most of mechanical and aerospace engineers are working at many important projects like aviation aircraft engine, and GE gas turbine, and GE wind turbine, and oil and gas turbo machinery, and healthcare. And GE Global Research Center is somewhere between university national lab and pure business units. So our job is to find out great ideas that often coming from universities and national lab and do some feasibility test of the idea and to turn the ideas into technology and then transfer the technology into products. So we are supporting the business and our annual funding size around $800 million. So I have very broad research experiences. For aerodynamic research, I have worked on wind turbine Air Force CFD. Also, I worked on wind turbine rotorcraft aerodynamics, and I also worked on turbo machinery CFD. And aeroacoustic research, I have worked on rotorcraft noise at Penn State, and also I worked on wind turbine noise, and I also worked on aircraft engine noise. So among these topics, today I'm going to present wind turbine aerodynamics and wind turbine noise. So I'm going to introduce to you wind energy first. Then I'm going to talk about wind turbine aerodynamics. Then I will present wind turbine aeroacoustics. Finally, conclusions and future research plans. This is global electricity usage map in 2007. Here is the US, maybe Davis is Northern California here. And so over the last decade, about 22,000 gigawatt has been newly installed globally. So over the next decade, we can expect the energy demand will be doubling. This is expected energy power in 2030. So you can see significant growth of energy power demand, not just in the developed countries like the US and Europe, but also in underdeveloped or developing countries like Latin America or Africa, India, or China, etc. Okay, this is 2007. So you can see almost a black in the Africa, and here bright lights here, India and China. You can see here very bright picture here, 20. So energy demand is huge in the future. The wind energy has played a significant role in providing the future energy. So in 2005, the global wind energy was just about 58 gigawatts. So now the wind energy has become more than 300 gigawatts globally. In United States, about 60 gigawatt of energy comes from wind. This is equivalent to 52 coal plants in the United States. So over the last decade, we have seen significant price drop. In 2002, the wind energy price was 15 cents per kilowatt. In 2012, the price was down to 5 to 7 cents per kilowatt. And wind industry market was about $5 billion in 22, but it has become about $50 billion in 2012. And reliability and efficiency has significantly grown. And wind energy was just about 0.4% of electricity in 2002. Now it provides about 4% of global electricity. So what's more important is this wind energy will be exponentially growing in the coming decades. For example, the Department of Energy says that about 20% energy will be coming from wind by 2030. So it might be too optimistic to say that the wind energy will be single dominant energy source, but it can be probably second or third dominant energy source. It will generate more than 20%, more than 30% energy. So it is huge enough to change the energy portfolio and energy policy. So one key driving element in wind energy is blade aerodynamics. This simple momentum theory explains how wind turbine works. So let's imagine that the wind velocity is coming from left to the right in this figure with a velocity u sub 0. And the wind velocity is reduced to certain amount of velocity as it passes through the wind turbine because the kinetic energy of the wind is extracted by the wind turbine. Here, wind turbine is modeled as actuator disk for this simple theory. So I want to introduce a very important concept here, which is called axial induction. The definition of axial induction is the ratio between u sub 0 minus u sub disk and the u sub 0. So it means how much the wind velocity is decelerated as it passes through wind turbine. So let's think about two extreme conditions. The first case is if there is no wind turbine, the wind velocity remains the same. In that case, axial induction becomes 0. And another extreme case is if the wind turbine stops the wind velocity completely, then this velocity at the turbine becomes 0. In that case, axial induction becomes 1. So axial induction is bounded between 0 and 1. So I'd like to ask you to remember this concept of axial induction because I'm going to talk a lot about axial induction in my presentation. So if we know the axial induction, we can calculate the momentum change. From the momentum change, we can compute the thrust and torque. And here is function of axial induction A. Also, you can see A prime, which is called tangential induction, and which is a similar concept as axial induction. So let's take a look at in one step deeper. It's the blade element or airfoil sections. So here, the incoming velocity is reduced by amount of axial induction A here. Also, in the rotor plane, there is a tangential velocity component, which is function of omega r, RPM, and there is A prime tangential velocity, tangential induction component. From this velocity triangle, we can compute the flow angle phi here, And the beta is the blade setting angle, which consists of collective blade pitch angle and local blade twist angle. So from the information of the phi and beta, we can compute angle of attack alpha. So for very high wind condition case, this velocity component is increasing. So this gives very high value of phi or high value of alpha. So angle of attack becomes very large for high wind speed. So in that case, we need to increase the beta. In that case, we need to increase pitch angle, blade collective pitch angle to reduce the angle of attack and to avoid blades, the flow separation. In the inboard section of the wind turbine, omega r becomes small because r component is small. In that case, again, the flow angle phi becomes large, or the flow angle of attack becomes very large. So in that case, we need to increase beta, which is blade twist angle at the inboard. So that's why we need to increase blade twist angle typically at the blade root section. So if we know the angle of attack and flow angle phi, we calculate the lift and drag, and then we can compute the thrust and torque. The next step is we can combine these two theories. One is momentum theory, and the second is the blade element theory. The thrust and torque that comes from the momentum theory should be the same as the thrust and torque that coming from blade element theory. So basically, we have two equations, thrust and torque, and we have two unknowns, axial induction A and tangential induction A prime. So we can basically solve this nonlinear equation, two equations, two unknowns. However, there are caveats we need to be very careful. We didn't consider the blade tip loss effects, and also it does not work very well for high axial induction, simply because the momentum theory fails for very high axial induction case. So we implement the Prandtl tip loss model and ground empirical correction to complete this method. So by the way, this method is called the BEM, boundary element momentum method. The fundamental idea is the simple. So if we know the blade geometry and rotor RPM, pitch angle, wind velocity, we can compute angle of attack, CL, axial induction, thrust, and power. There is another more accurate method for aerodynamics, which is the vortex line method. This is called the VLM. The vortex flow that comes from the rotating blades induces the velocity on the rotor plane. This induced velocity can be calculated by standard Biot-Savart law. So here gamma is vortex strength or circulations. So once we know the induced velocity, we can compute the angle of attack from the previous the chart, the same the velocity triangle. And also we can compute the polar data from the angle of attack, CL. So once we know the CL, we can use the Kutta-Joukov theorem to compute the circulation gamma. So once we know the circulation gamma, we can come back to the previous step to update this induced velocity. So this process is repeated until we get the correct value of the gamma and induced velocity. But the input and output are the same. So if we know the blade geometry, rotor RPM, pitch angle, wind speed, we can compute angle of attack, CL, and axial induction, thrust, and power. So far, I have covered basic elements of wind turbine aerodynamics. Now I'm going to talk about blade design. So here I split the blade design process into 3 steps. The first step is to determine optimal operating condition, and the second step is to determine design aerodynamic performance, and the third step is determining blade geometry. So wind turbines start to generate the power beyond the threshold of the wind speed. That's called hot wind speed, and it's generating power, and then reach the maximum of the power and the operation stop at very high wind speed. That's called cut-off wind speed. This is RPM of the rotor blade. So when it starts to rotate, it's generally linearly increasing as a function of wind speed, and then it reaches the maximum value and remains constant. Here is another important parameter, which is called tip speed ratio, which is simply the ratio between blade tip speed and wind velocity, incoming wind velocity. In the linear region of the RPM, so we have constant value of tip speed ratio. This tip speed ratio is very important in terms of the power coefficient. And this is pitch angle. So pitch angle remains constant up to at a certain amount of wind speed. At very high wind speed, we need to increase the pitch angle because we want to avoid the flow separation. That's what I discussed earlier. And this is a CP, or power coefficient. And CP remains the maximum for the constant tip speed ratio and constant pitch angle. And so then CP drops at very low speed and it drops at very high speed. So it's very important to determine the right value of tip speed ratio and pitch angle. The second step is design of aerodynamic performance. The wind turbine blade typically consists of 8 to 10 airfoil sections. So at each airfoil section, we want to achieve the maximum lift to drag ratio from the best aerodynamic perspective. The lift and drag ratio is a function of angle of attack. So we like to find out the optimal angle of attack such that we can maintain the lift and drag ratio at each blade sections. If we know the optimal angle of attack, we can find optimal lift coefficient here. And theoretically, the maximum CP comes from the constant value of axial induction, which is 1/3, and this is called batch limit. But practically, it is impossible to maintain the constant value of axial induction because we need to consider tip loss effect and root loss effect. Also, structure point of view, the constant axial induction is not the best solution. However, we like to maintain the 1/3 of constant axial induction for the most part of the blade, and we need to give some variation at the tip and variation at the root. The third step is to blade inverse design. So in the normal analysis mode, as I discussed earlier, blade twist and cold are the input, and desired lift coefficient and axial induction are the output. But in this inverse design process, this input and output are reversed. The input is desired lift coefficient and axial induction, and the output is blade twist and cold. So mathematically, this is a root finding problem, and multidimensional Newton method works very well for this case. And this is multidimensional Newton method. So unknown is x. So x is the blade twist and cold distribution as function of the blade radius. And we want to find out the x star, the solution, such that f becomes 0. This f is defined as the difference between desired value and predicted value. So we can find out this solution in an iterative fashion. So xk plus 1 times that, so we can iterate this one. And J is Jacobian matrix, which is given by this term. So I want to summarize what I have discussed so far. So we start from the optimal tip speed ratio and pitch angle, and then we prescribe desired CL and axial induction from aerodynamic perspective. Then we can start with initial guess of twist angle and cold, and then we run the BM and BLM. And those are I have discussed earlier. And then we check the calculated CL and axial induction meet the desired target or not. If not, we can solve the multi-dimensional Newton method to update the blade code and twist and rerun the VM and VLM. So this process is repeated until we get the converged solution. Once I developed the program, computer program to solve this process, unfortunately this didn't work very well at the first time. This is example. This is twist angle as function of blade radius, normalized radius. So we want to achieve the blade twist in solid line, black solid line. In the middle section, pretty good, and at the tip, it's pretty good. And by the way, we start with this linear function as our initial guess. The problem occurred at the root region. So we have some outliers here. And I investigated this problem and I identified this problem is associated with the flow separation. So whenever flow separates on the blade, CL, the lift coefficient behavior, something like that, there is a linear region and increase in CL as a function of angle of attack, and then it decreases because of the flow separation. So our goal is to determine angle of attack such that we can get the desired target. But whenever the flow separates, we have multiple solutions of angle of attack, not just in the linear region, but beyond the linear region, we can get the different solution. So it's a non-uniqueness problem, mathematically speaking. So in order to solve this problem, I treated outliers as numerical oscillations and applied numerical filtering. After we solved this standard multi-dimensional Newton method, I applied the spatial averaging, which is equivalent to low-pass filtering, in every iteration of Newton method. This theta, x theta is average value, and x without theta is low value. So every iteration of multi-dimensional Newton method, I compute x theta. This becomes input in the next iteration. This is result with the spatial averaging, green lines. So I can successfully eliminate these outliers, so I can get the very smooth results and what I expected. So this is the example of blade design. So let's assume our target of tip speed ratio is 9 and pitch angle 0. And this is our desired CL and actual induction. So I use the BEM design, BLM design, both give excellent agreement with the desired target. From these desired values, I come up with the twist and chord blade geometry, which is our output. So both codes give almost identical results. Although there are small discrepancy here, the general is pretty good, so we are very happy about this performance. So now we develop this design code and transfer the technology into the business, and now GE Renewable Energy business are using this design tool to make the next generation of wind turbine blades. Okay, this is my second topic, which is yeah.
Your tool, you use only inviscid
Yeah.
viscous effect is not important?
It's not included here. Viscous impact is somewhat indirectly included in the polar data. So the polar data, the CL as a function of angle of attack, that comes from CFD or experimental data. So that includes some viscous effect indirectly. Okay, the second topic is wind turbine noise. So one big downside of wind energy is wind turbine noise. This is a noise complaint from a resident of Fox Island in Maine State here, in this East Coast area, where 3 big turbines are installed. I think residents are living somewhere around here. There are resident areas. So he says the excessive noise an indicator of poor performance. And he claimed that due to the wind turbine noise problems, local residents are voting to keep turbines out of their towns. The wind industry will continue to have a major fight on their hands if they want to use land-based turbines as a renewable energy source in rural communities. So you can sense the significant issue of this problem. One journal paper reported out the wind turbine noise is much more annoying than any other type of noise sources. So for the given sound pressure level, the wind turbine noise shows much higher percentage of highly alien compared to other noise sources, aircraft, road traffic, and railroads.
If you earn money with that wind turbine, that graph sure shifts all the way to the right.
That's what we So this is based on the survey of the residents. So it's real data. So I want to talk
How
about
about the intensity of the noise?
Yeah,
Forget
yeah.
about annoyance.
yeah,
You
that's
can measure the
that's
intensity.
a good question. So intensity is related to sound pressure level. So intensity, let's pick a one intensity here, 46 dB. The same energy intensity, but people listen differently. So it's because of wind turbine, it's very annoying. It's because of it's constant and it's related to motion of the blade. When it rotates, it causes very annoying noise. It's a swish, 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 swish. It's constant. So people complain. Yeah. The aircraft noise and traffic noise in railways does not have that kind of large fluctuation, but wind turbine noise is a fluctuation. If you get the average value intensity, it's not that large. But if you hear the noise variation, it's really annoying. So then what is the physical mechanism of the wind turbine noise? The main aerodynamic noise source is edge scattered noise by turbines. This is a wind turbine blade airfoil. The pressure fluctuation in the turbine boundary layer is scattered by trailing edge, sharp trailing edge. So basically, the hydrodynamic energy is converted into acoustic energy by the sharp trailing edge here. So it's kind of acoustic scattering problem. And Fox, Williams, and Hall derived analytic solution for this type of problem. They used the simple model of the turbines here. They used the infinitely thin plate as a scattering body, and they calculate acoustic energy by the scattering by edge here. It's not exactly the same problem, but it gives some insight into the physics. They show that acoustic energy is proportional to the fixed power of the Mach number. So if you think about the wind turbine, so the highest Mach number occurs at the blade tip because of the rotation of the wind turbines. So most of aerodynamic noise is generated near the blade tip. So that explains by these equations. So I talk about the main noise source is acoustic scattering by the trailing edge. So GE modified the trailing edge geometry to reduce the scattering effect. So this is serrated blade trailing edge. We changed the blade geometry trailing edge, only near the blade tip. So we don't need to do at the blade root because that's not the noise source. So you can see how big is compared to this person. So there's a serration installed, and we measure the noise, and this is the summary of the noise reduction. So we tested 1.5 megawatt turbine and also 2.75 megawatt turbine at different frequencies, 500, 1 kilowatt, 2 kilohertz. And whatever left about is noise reduction by this geometry. So here 0 means there is no change of the noise. and minus value is the noise reduction, and actually positive value is noise increase. So in generally, we can achieve noise reduction by 2 and 4 dB but at the 500 Hz and 1 kHz. Maybe 2 kHz may not be perfect, but in generally, in these areas, we are getting very good results without any aerodynamic performance degradation. The same power performance noise reduction. So I have discussed the issue of wind turbine noise, what is general mechanism, and how to reduce noise. Now I will show you more detailed equations, theory, and prediction method. So Fox-Williams-Hawkins rearranged the fluid mechanics Navier-Stokes equation and generated acoustic analysis formulation in 1969. So this is a Fox-Williams-Hawkins equation, very simple form. And left-hand side is a wave operator with respect to acoustic pressure. The right-hand side is acoustic source term. The first term is called the thickness noise. The noise is generated by displacement of fluid because of the motion of the body. If the body is stationary, there is no motion, this noise is not generated. The second term is loading noise. This is caused by unsteady loading fluctuation on the blade. So lift and drag is very important in this loading noise. And the third term is quadruple source, and this includes all nonlinear source terms like shock waves or the nonlinear volume sources. And once the noise is generated by this process, it propagates with the speed of sound in the unbounded domain. But whenever the object exists, the noise is interacted with the body, and then scatter wave is generated. So it's important to solve the boundary condition if we want to solve this problem. Typically, the boundary condition is given as pressure gradient. And this is called acoustic scattering problem. There are lots of applications for this. For example, aircraft engine noise is interacted with the fuselage body. Helicopter rotor noise is interacted with the fuselage. I discussed the wind turbine application. The noise is generated by the scattering by sharp edge here. At the end of my talk, I'm going to show the scattering of rotorcraft noise as just an example. So again, the problem is to get the pressure gradient on the body. That's kind of an important input. So we can think about this Fox-Williams-Hawkins equation because it gives some pressure, acoustic pressure. And Faraset and Nazareni gave analytic solution of the pressure, acoustic pressure using free space Green function. This is acoustic pressure. It's expressed as integral term here. I'm not going to show all the detailed components, which is not relevant right now. But all the components as calculated at the retarded time or source time. The easiest way to compute the pressure gradient you can think of is just to take the gradient on both sides. So pressure gradient here and gradient of outside integral. So it looks easy enough, right? But it's not. It's very difficult to compute this stuff. And when I was a PhD student, and my other guys called me one time, and he gave me this problem. He said, I got a funding from NASA to solve this problem, but I know that I don't like this one. I like better one. So that is your job. So you need to give me better solution. So that was my first work at my PhD. So I went back to the previous work, Fox-Williams-Hawkins equation and Faraset formulations. And this is again the Faraset formulation of acoustic pressure. and I used this conversion. The pressure gradient can be converted into observer time derivative. So with that, I got the observer time derivative outside the integral. So instead of having gradient form, I have the time derivative outside integral. This makes much easier to compute this term, but it's not complete. It's called, so I call it semi-analytical form. So this is called, I name it formulation G1. I did one more step. I converted the observer time derivative into the source time derivative. So the observer time means the time when the observer received the sound. The source time means the time when the acoustic is actually generated. So there is some time delay between observer time and source time, which is a function of the speed of sound and the distance. The beauty and the benefit of this conversion is we can take the source time derivative inside integral and then take the source time derivative each component here, which is also calculated at the source time. So this gives a full analytic solution of the pressure gradient. So I name this one formulation G1A. So if you are interested in detailed equations, so you can find out the journal paper. So this is one validation problem. I solved the helicopter noise problem. This is acoustic pressure and three components of the pressure gradient. So I'm showing three calculations. Finite difference method. This is simply the gradient operator outside the integral, and there are two formulations. Basically, they are giving the same solution. So is there any benefit with this term? Because I'm getting the same solution. Yes, I have benefits. So I look at the computation time. There's huge difference. So formulation 1A, this is just for acoustic pressure, and these three terms give pressure gradient. The same solution, but very different computation time. So formulation G1A, which is a purely analytic solution, reduce the computation time by a factor of more than 2 compared to finite difference method, which is the gradient operator outside the integral. So I got the pressure gradient accurately and efficiently, and then my next step is solving acoustic scattering problem. Historically, this was solved in the frequency domain, but I have generated time domain acoustic scattering method, which has more beneficial for broadband noise or impulsive noise, any type of noise sources. So I want to give you very briefly the concept of this method. So my idea is to put the equivalent or imaginary sources inside the scattering body. So there's imaginary sources here, and the strength of the imaginary sources is determined by the boundary condition on the scattering body. So this is boundary condition, the equation here. The Q is the source strength of the nth equivalent source. We have multiple points of the equivalent source. Each has different source strength. And the right-hand side is pressure gradient, which I computed just a minute ago. And the source strength is discretized at each time step. So we can compute the source strength at each time step. And then once we know that, we can compute scatter waves, so that then we can solve the problem. This is example of acoustic scattering of rotor clamp noise. We have 4 rotor blades and 2 tail rotor blades and representative fuselage. And I placed observer plane about 10 meters below the helicopter to look at the sound pressure level productivity. This is a fuselage geometry. I got this from NASA Raymond because it was supported by NASA Raymond. And this, I generated equivalent source geometry, which are basically embedded in the scattering body. So I determined the source strength of the equivalent sources. That gave me the solution of the scatter field. So I'm going to show you some examples. This is sound pressure level at 3 times tail rotor blade passes frequency. For the simplicity of the problem, I'm going to show you only tail rotor problem. This black solid line is the projection of the tail rotor. So you can see high noise level is of course in the tail rotor plane, and very low noise level at the side rotor. Now I have included the fuselage, and I can see there's a little bit complicated pattern, noise pattern, but more importantly is the increased noise level at the side wall. It's because of the acoustic energy is scattered by fuselage and propagated this way and this way. So scattering effect is really important in this problem. And once I computed this one, I compared with a different code which was developed NASA. It's called NASA fastest scattering code. I compared two results. It's almost identical. So this gave me additional confidence that my code works very well. It's two different codes giving the same results. So this is conclusions on my talk. So I developed an aerodynamic blade design approach for wind turbine blade. So I discussed about wind turbine noise, the issue, and the scattering problems, and then I showed the analytic solutions of the acoustic pressure gradient and time domain acoustic scattering method. And I'm going to talk about a little bit about my future research plans. So I like to work on fundamental and scientific research on applied aerodynamics. But at the same time, I will always try to find out ways to apply my research into real-world problems like wind energy, aircraft engine, rotorcraft, or aeroacoustic problem. For example, wind energy, I'm interested in active flow control to improve performance and reduce noise. Since I have very broad interest, broad application, I'm confident that I will have a lot of opportunity to get research funding. For example, for wind energy, I'm going to work for Department of Energy, NSF, or GE. And for the propulsion rotorcraft, I'm going to work with Department of Defense. And for the aeroacoustic, I work for NASA. So based on the excellent research environment at UC Davis, I can find out many collaborative opportunities with the different faculties, like wind energy, turbomachinery, aerodynamics. So I'm also interested in collaborating outside UC Davis, like industry, GE, Siemens, Pratt Whitney, or some Korean companies like Samsung, Hyundai, Doosan, etc. For the national lab, I'm very interested in collaborating with NRL Sandia for wind energy and NASA for aeroacoustic. And Penn State has very strong reputation in aeroacoustic and rotorcraft. I'm very interested in working with them. So this is my teaching interest. So I'm very interested in teaching traditional aerospace undergraduate courses like propulsion, aerodynamics, fluid mechanics. I'm also interested in teaching advanced graduate courses like aeroacoustics, wind energy aerodynamics, or rotorcraft aerodynamics. Okay, thank you for your attention.
Questions for Dr. Lee?
Can you apply your acoustics methods to launching rockets? Because NASA is very interested. The problem now, you have highly compressible. So can you count for shock waves?
Yeah, I think it's very good suggestion. So I think it's very interesting problem that the rocket, exhausts the high velocity flow field and turbulence generate noise and it propagates upward and it's interacting with the body, right? So that causing some electricity problem and some structural issues. So I think that's a good opportunity for research. Absolutely.
Any restriction in your method to account for shocks?
It's actually my method is split the the source mechanism and the propagation mechanism. So source mechanism can comes from any type of the CFD numerical simulation. Once I get the source, I can plug in my acoustic scattering propagation. Then I can only deal with the propagation part. So I think that's very efficient rather than solving the entire problem in one package.
Is the blade tower interaction in the wind turbine, is that producing low frequency noise? Is that also bothering?
Especially that's very concerning issue for downwind turbines. So downwind turbine, the rotor blades behind the tower. So tower generate the waves that hitting the noise. I think that was big concern, and especially NASA was very interested in that problem in 1980. So in 1980, there were a lot of research in the downwind turbine because of their very benefits in the downwind turbine, but the program was stopped because of the noise issues. So we need to solve the noise issue. We wanted to install downwind turbine.
Question about you showed on the turbine, you showed the turbulent bound layer interaction with the trailing edge, of course, and that is I would say is and also one more difficult part to solve. I think like the serrated trailing edge is I think we mostly developed that. I think empirically. I think I haven't seen too many computational attempts, or maybe attempts have been done, but I haven't seen any computational results from that. Can you comment on that?
Yeah, that's actually true. So I show the success story of GE, the serrations, we were able to reduce noise. That's heavily based on the experiment, not the numerical study.
Any explanation?
We don't have a good trust on the numerical simulation.
No, not the explanation. Why it happens?
Then,
Why these shapes reduce noise?
Okay. So simple answer is change the scattering effect. More complicated, more difficult answer is we change the correlation of the turbulence in the spanwise. So it breaks down the correlation of the turbulence in the spanwise because of these serrations. So that basically changed the effect of the scattering. So going back to the questions, I think, so right now the design is heavily rely on the experiment. So because we trust the experimental results, but at this time, the numerical results, we do not fully trust the numerical results. But that's a big area actually. We are doing a lot of work. So we never gave up the numerical predictions. So we are hopefully, I don't know how many years will come, but we are working on that.
You showed that interesting study of the difference between essentially the influence of perception on what people find annoying. And it seems to me that on that plot, being able to reduce the intensity of the acoustic intensity by a couple of decibels may not go a long way. I mean, it looks like you have to actually work on the perception more than anything else.
Yeah, I think there are two topics. First, we need to reduce the noise dB, 2 dB or 4 dB. Maybe that does not go push enough to right hand. The second part, we need to reduce the modulation part. Not just average dB scale, but the variation. So that's also a very significant part. That's called amplitude modulation. That's a big topic in wind turbine noise. So not just reducing noise, but also how can we reduce this modulation?
Okay, I think with that, thank you so much for your presentation.